Imagine for a moment you had a magic flashlight, and whenever you shine the beam on an object, that object would be drawn toward the brightest area of the beam, in this case, the middle. The force on the object is derived solely from the light emitted from the flashlight, not from an equivalent counterforce on the mass of the flashlight itself. In physics, the process is called optical trapping, or optical tweezers. It is typically used to manipulate nanoparticles or microscopic samples with laser light. Research in this area won the Nobel Prize in Physics in 2018. We'll discuss the nature and magnitude of the forces in just a moment, but, in principle, such an arrangement could be particularly useful in space applications. All you need to do is shine the beam slightly in front of the nose cone of your rocket. The nose cone, the rocket, yourself, and the flashlight are drawn forward toward the brightest area of the beam. As long as you keep the flashlight directed slightly ahead of the nose cone, you can coax the ship along indefinitely. That seems like quite a stretch, but let's look into it. There are two phenomena at work in optical trapping: photon scatter and optical gradient forces. Photon scatter is measurable on the microscopic level because photons do have some momentum. When photons bounce off, reflect, or refract from a body, they can transfer some momentum, and that can give rise to an observable force. The force manifested due to scatter tends to be quite small, so we'll focus on the second phenomenon, optical gradient forces. We'll consider the case where the radius of the target is less than 1/4 the wavelength of the laser light. In such a case, and when the electric susceptibility of the material is amenable, the electric field of the passing laser light will induce a polarization in the target. Positive charge will collect on one side and negative charge will collect on the other. A dipole will form. This will happen with each passing antinode of the laser light, and the dipole will alternate direction. But here is where it gets interesting. When the dipole forms, it finds itself in an asymmetric electric field, a gradient. The upper edge of the dipole experiences a stronger electric field than the lower edge of the dipole. Because of the gradient, there will be a greater force on the upper end of the dipole than on the lower end, and the sample will be drawn along the gradient to the area of highest optical intensity. The effect is the same for the opposite antinode. The electric field has reversed, consequently the dipole has reversed, but the gradient has not. The result is that the object is again drawn to the area of highest optical intensity. In the end, because of the high electric field and the presence of the optical gradient, the target feels a small pulse with each passing laser antinode. The result is a cumulative force on the target mass derived solely from the electric field of the passing light. Now, the force upon a micron-sized object under typical conditions is extremely small, on the order of piconewtons. But that is a result of the fact that the differential charge driven on the object is also small, the equivalent of a relative handful of electrons. On the other hand, the electric field of a laser, even a 10 milliwatt laser, focused to a 1 millimeter spot size, is phenomenally high, on the order of 1 kilonewton per coulomb. That gives us an opportunity to achieve forces on a potentially useful scale, if we can access the electric field efficiently. Optical trapping is a tool for the manipulation of microscopic particles in 3 dimensions. For the purposes of this application, we are only interested in manifesting the force in 1 dimension. That means we don't need to limit the shape of the target to a sphere or stay on the microscopic scale. We can use an extended sample, like a wire, still keeping the radius of the wire less than 1/4 of the laser wavelength. Using a wire, we can drive a much higher differential charge over a much longer path, say a factor of 1000, for a 5mm length of wire and a 5mm beam diameter, thereby increasing the force we expect to measure to the order of nanonewtons. Additionally, we can use a multiplicity of wires over an optical path length of a meter or more. By retroreflecting the laser, it is possible to have 10 to the 6th of 10 to the 7th interactions, still in a relatively small device. With an approach like this, it seems quite possible to achieve device performance comparable to or exceeding other small-scale engines for space applications. That being millinewtons of thrust from watts of power in a kilogram scale device, 1 to a few hundred cubic centimeters in size. The advantage of this approach is that the thrust source, the laser, is rechargeable, say from a solar panel, and so may provide total device lifetime output measured in Newton months or years, instead of Newton hours. But that's just the beginning. Since the approach is scalable and available laser sources are small and inexpensive, it is reasonable to expect to apply kilowatts of optical power and achieve kilonewtons of force for more demanding applications. We hope this has given some sense of a different approach to the problem of spaceborne propulsion. Thank you for your attention.